Welcome to G Fun Facts Online. Today we are going to unravel a story that sounds like science fiction, but is historically and mathematically true. It is the story of a man who, quite literally, heard the universe. We are traveling back to the early 20th century, to the dusty, humid town of Kumbakonam in India. Picture a young man sitting on the porch of a small public house. He is poor, often hungry, and entirely cut off from the elite academic circles of the West. He has no formal training in advanced mathematics. And yet, he is scribbling furiously on a slate, erasing calculations with his elbow, and writing down equations that no human being had ever seen before. To him, these numbers were whispers from the goddess Namagiri. To the rest of the world, they would eventually become the keys to understanding the very fabric of our reality, from string theory to the event horizons of black holes. This is the story of Srinivasa Ramanujan. Let's dive straight into the impossible genius of this man. To understand why modern physicists are obsessed with his notebooks today, we first have to appreciate how unlikely his existence was. Ramanujan was born in 1887. His primary mathematical resource was a dusty old library book called Carr's Synopsis of Elementary Results in Pure and Applied Mathematics. Now, this book wasn't a textbook. It was just a list of 5,000 theorems with almost no explanation of how they were derived. Most students would have used it to memorize formulas for an exam. Ramanujan used it as a launchpad. He looked at the gaps between the theorems and began to fill them with his own intuition. Because paper was expensive, he did most of his work on a slate, recording only the final results, the gems, in his notebooks. In 1913, he took a massive gamble. He wrote a letter to G.H. Hardy, the most famous mathematician in England at the time. Imagine receiving a letter today filled with gibberish-looking equations from an unknown amateur. That is what Hardy received. It was a mess of wild formulas, infinite series for pi, and strange assertions about prime numbers. Hardy's first instinct was to throw it in the trash. He thought it was the work of a crank, but he kept looking. He saw a formula for continued fractions that defied logic. He later famously remarked that these formulas must be true, because if they were not true, no one would have the imagination to invent them. That letter started one of the most romantic and tragic partnerships in the history of science. It was a clash of two worlds. You had Hardy, the rigorous atheist who demanded a proof for every single step, and Ramanujan, the devout Brahmin who claimed these theorems were placed on his tongue by a goddess. One of the first places Ramanujan revolutionized mathematics was in the calculation of pi. For thousands of years, humans have struggled to calculate digits of pi efficiently. The old formulas were slow, but Ramanujan saw pi differently. He didn't see it as just a geometric ratio. He saw it as a deep spectral value arising from complex modular functions. In 1914, he published a formula for 1 divided by pi that was bizarrely fast. To a standard mathematician, the formula looks like a random collection of numbers. It involves the square root of 2, the number 9801, and the number 1103. Why those numbers? Why 1103? It seemed random. But it wasn't. This formula was a modular machine. It adds 8 decimal places of accuracy for every single term you calculate. If you calculate just the very first term, you already have pi correct to 6 decimal places. This level of precision was unheard of. Years later, in 1985, William Gosper used this exact formula to calculate a then-record 17 million digits of pi. Today, almost all supercomputer records for calculating pi rely on what we call Ramanujan-Sato series, which are derived directly from this insight. Ramanujan didn't find this by crunching numbers. He found it by understanding modular equations, functions that stay symmetric when you fold and stretch the complex plane. He didn't know it at the time, but he was building the toolkit for string theory. And this is where our story shifts from pure math to the bedrock of modern physics. We need to talk about the number 24. In the 1960s and 70s, physicists began developing string theory. This is the idea that the fundamental particles of the universe, like electrons and quarks, are not tiny dots, but tiny vibrating strings. But there was a major problem. The math kept breaking. When physicists tried to calculate the probabilities of these strings moving through space, the equations produced anomalies. They were getting results like probabilities greater than 100%, or infinite energies. Mathematical nonsense. To fix the math, they realized the strings needed room to vibrate. They couldn't just vibrate in our 3 dimensions of space, plus 1 of time. They needed more dimensions. But exactly how many? When physicists sat down to calculate the critical dimension for the original bosonic string theory, they encountered a strange sum in their equations. It was the sum of all natural numbers, 1 plus 2 plus 3 plus 4, and so on, to infinity. Intuitively, you would think the answer is infinity. But in the weird world of zeta function regularization, a technique Ramanujan was a master of, this sum behaves as if it equals -1/12. To make the physics consistent, specifically to preserve something called Lorentz invariance, the dimension of the universe had to satisfy a specific equation involving this sum. When you solve that equation, you find that the dimension minus 2 must equal 24. Therefore, the dimension must be 26. The universe of bosonic string theory must have 26 dimensions. Where does the number 24 come from? It comes from the Ramanujan modular discriminant. Ramanujan was obsessed with the number 24 decades before physicists even dreamed of strings. It appears in the Theta function, a modular form Ramanujan manipulated with ease. The 24 modes in the Ramanujan function correspond exactly to the 24 physical vibrations of a string in the transverse directions. As the famous theoretical physicist Michio Kaku once noted, the string vibrates in these dimensions because it requires these generalized Ramanujan functions to remain self-consistent. It is as though a deep numerology is being manifested in these functions that no one fully understands. Even in modern superstring theory, which reduces the dimensions from 26 to 10, the math still utilizes a generalization of Ramanujan's work. But the most chilling chapter of Ramanujan's legacy comes from his deathbed. In 1920, Ramanujan was back in India, dying of illness. He was in pain, wasting away, yet his mind was more active than ever. In his final letter to Hardy, dated January 1920, he wrote about a new class of functions he had discovered. He called them Mach theta functions. He wrote that unlike false theta functions, these entered into mathematics as beautifully as the ordinary ones. He listed 17 examples, gave no proofs, and then died. For decades, these functions were a mystery. They didn't fit into the standard definitions. They were almost modular, but they had a shadow, a chaotic term that ruined their perfect symmetry. The mathematical community largely ignored them. They were viewed as the final, confused scribbles of a dying genius. That changed in 1976. American mathematician George Andrews was digging through a box of old papers in the Trinity College Library in Cambridge. He found a sheaf of papers with Ramanujan's distinctive handwriting. It was the lost notebook. The discovery was electric. Andrews described it as the mathematical equivalent of finding Beethoven's 10th Symphony. It contained over 600 formulas, mostly focused on these mysterious Mach theta functions. Fast forward to the 2000s. Physicists were trying to solve one of the biggest paradoxes in science: black hole entropy. Stephen Hawking had famously predicted that black holes have entropy, a measure of disorder. But in quantum mechanics, entropy is a count of microstates, the different ways the insides of the black hole can be arranged. To prove Hawking right, string theorists needed to count these microstates for a specific type of black hole. When physicists Atish Napolkar, Samir Murthy, and Don Zagier looked at the math required to count these quantum states, they were stunned. The equations governing the entropy of black holes were exactly the Mach theta functions Ramanujan had scribbled on his deathbed. Ramanujan's Mach symmetry was precisely the tool needed to describe the imperfect modularity of a black hole's quantum states. He had discovered the mathematics of black holes 50 years before the concept of a black hole was even fully accepted by physicists. No discussion of Ramanujan is complete without the story of the taxicab number, which perfectly illustrates his relationship with numbers. While Ramanujan was ill in Putney, Hardy visited him. Hardy, awkward as always, arrived and said, "I rode here in taxicab number 1729. It seemed to be a rather dull number." Ramanujan, lying sick in bed, immediately replied, "No, Hardy, it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways." He knew instantly that 1729 is equal to 1 cubed plus 12 cubed, and also equal to 9 cubed plus 10 cubed. He didn't calculate this in his head at that moment. Ramanujan simply knew the number 1729. To him, numbers were personalities. Today, 1729 is known as the Hardy-Ramanujan number. And curiously, this number also appears in string theory and the physics of K3 surfaces, which are shapes used to compact extra dimensions. It seems that even his little jokes with Hardy had deep roots in the structure of reality. Today, Ramanujan's influence extends far beyond theoretical physics. We use Ramanujan graphs to build efficient communication networks for the internet. His algorithms drive the computer algebra systems we use for research. His work on crystallography helps chemists understand the structure of matter. Ramanujan always attributed his success to his family goddess Namagiri. He famously said, "An equation for me has no meaning unless it expresses a thought of God. Whether you believe in the divine or in the subconscious processing power of a singular genius, the result is the same." Ramanujan tapped into a vein of mathematical truth that runs deeper than human logic usually allows. Srinivasa Ramanujan died at age 32. He left behind 3 notebooks and a pile of papers that were lost for half a century. He never saw a supercomputer. He never heard of a black hole. He never knew what a string was in the context of physics. And yet, when we push the boundaries of human knowledge today, when we try to count the states of a black hole or map the 10th dimension, we find Ramanujan there, waiting for us. He had already sketched the map. His legacy teaches us that mathematics is not just something we invent to describe the world, it is something we discover. It is the code of the universe, and Ramanujan was its greatest hacker. Thanks for listening to G Fun Facts Online.